The main reason I bought a 3D printer was to build camera gear, so I think it's time to focus on that original goal, do some practical printing, and maybe learn something new. Good morning. It's been a while, but I'm back, and today I want to talk about lens gear rings and how to make them out of TPU. If you haven't tried printing TPU yet, it's really fun, and on the Elegoo Neptune 2S you can print it without having to upgrade. Okay, I wish this camera had a clicky button, but I'm also working on that. I'll share this once I make a little bit more progress, but the prototype is working. If it's your first time to see one of these gear rings, they slide onto the focus ring of your lens, and then what it does is it allows us to control the focus like this using a follow focus, instead of having to touch the lens and turn it like this, which gives us a lot more stability and a lot more control over the focus. Then what I have is a wireless version. And this is connected by Bluetooth to a motor on my lens. And when I turn this knob, it turns the focus ring for me. This one is a Nucleus Nano made by Tilta. And this is a roll of 6-month-old TPU. I've been keeping it in... It's a little bit noisy to try to talk and do that at the same time. I've been keeping it inside the plastic bag just like that for 6 months with a few packs of this silica gel. And it's really not the best way to keep TPU. But what I want to show today is that we don't have to be perfect. We can cheat. Depending on what we're printing and how we're printing, sometimes we can get away with cheating a little bit. And that's what we're going to do today. TPU is flexible and wear resistant. It stretches just enough to make it useful for this application. A harder plastic like PLA would have a hard time fitting over the lens while also holding the focus ring tightly. The extruder on the Neptune 2S has a reasonably small gear clearance, which allows us to print TPU easier and faster than some printers. One downside to TPU is that it does soak up moisture, so in general you should try a little bit harder than me to keep the filament dry. Let's start printing a ring, and then I'll show you how to design and make your own. And the cheating part is that we're going to use the same settings as PLA. There's only 2 differences. The first difference is that we're going to print at 220 degrees. The second thing that we need to do is raise the offset a little bit. When we print PLA, we try to get a nice smushed first layer to get good bed adhesion. But for TPU, if we smush so much, we'll get a giant blob as soon as the nozzle raises up. So what we want to do is we want to have the first layer be a nice solid thick line, not smushed down so much. And TPU does a really great job of sticking to the bed. So I'm going to raise the offset about 0.15 compared to normal. And then let's print out a 6mm gear. With the first layer we go a little bit slower. I do the same thing for PLA. We want good adhesion and have a solid foundation to work with. After the initial layers we run at full speed. Now you probably can't run every print this fast. The trick here is that we're avoiding travels, we're avoiding hops, and we try to keep the nozzle over the print surface. We always have some surface tension, which really helps with the flow. If we start doing big travels and bridges, we might end up having some trouble. So now let's take a look at the design process. I'm going to work with Fusion 360. So usually we need to go into this create menu and there should be a gear function available. But at the moment it's not available and we need to install it. We go over to utilities, click on add-ins, go go to add-ins, and we're going to add spur gear. Now when we go back to solids and into create, we should have a spur gear, but I installed the wrong one. So try again. Okay, this time it's correct. So we go to solid, create, and now we have spur gear available, and we open it up and we have the spur gear menu now. So there's a lot of options available with making gears, but we don't need to focus on all of them for this project. The pressure angle we're going to leave as is. The module is the important one for here. So if we have, for example, a follow focus system with a gear and we want to make a lens ring to fit and mesh together with that gear, then the module of both gears should be the same. I've looked it up on the internet and the Tilta system uses a module of 0.8. Sometimes it's referred to as mod or MOD. So I'll set my module to 0.8. Number of teeth is also going to be important, and if you know the math and you can do the math, then you can do everything by calculation, but we can play around and figure it out. Basically, we're going to need somewhere between 70 and 110 teeth. Should be good for most size lenses. So if I change the number of teeth down to 80, for example, then we'll see that the pitch diameter is also changing. And now I have a warning that the center hole is too large for the pitch diameter. So the hole diameter, so we need to take a pair of calipers, measure the focus ring, and then minus about 0.5 or 0.3. Here I have a focus ring that measures 82 millimeters, and I've set it to 81.7 millimeters. So I know that if I want to make this work, I'm going to need more teeth than 80. So we can see that 109 is working, and 104 is too small, it says. Let's try 105, and we'll see what happens. Backlash we'll leave at 0. Root fillet radius is this radius down here. And it says right here for us, actually. We'll leave this at 0.1. Gear thickness is completely up to you in your follow focus system. I made both 6mm and 10mm versions. We'll keep it at 10 for this sample. And now it seems like everything should be okay. So let's push OK and it'll generate a gear for us. And here we have our gear. But if we take a closer look, we're going to see that there's something a little bit strange. I'm not using a mouse, I'm trying to use my trackpad, which isn't the best idea. So we can see here, okay, like this is a little bit better. We can see that there's a gap created, and I think this is due to the order of operations when creating a gear. So first we're creating the gear circle, then it's subtracting the hole, then it's adding the teeth in after, and because it's adding the teeth in after, the teeth are not subtracted when the hole is subtracted from the original circle. And if we try printing this out, then it's not going to be correct. So let's just undo this gear and we'll try to make another one. So this time what I'm going to do is I'm going to put the hole diameter just to 10. And now we can see we have a gear that looks like it's formed well. The hole is too small, but we can deal with this easily enough. There's a hole command, but I prefer using sketching. It's easier for me. We create a new sketch. Then from the center, we'll make a circle the size of the hole that we want. Finish the sketch. Then we can extrude the circle down. And now we have the gear that we want. Now when we're printing, there's one more thing that we want to keep in mind. So this is a perfectly good gear. And let me open up Cura and I'll show you what I mean. So I want to print this gear using 2 walls and I want to try to avoid infill. We'll see here that there's a large amount of gap between the teeth and the inner walls of the gear. And we want to try to avoid this. So what we're going to do is we're going to change the number of teeth and hopefully we can avoid needing infill or leaving a gap. Actually, having a small gap isn't a big problem if you don't mind yourself. So for the gears that I'm using right now during making this video, there is a small gap in them, about 1 line width. And I didn't find that it affects performance. Let's try to make this pitch diameter smaller here. And let's see if we can calculate it roughly. So I'll put 3 walls And then I can see that it tries to print one wall in between here, and one wall is about 0.4. So 0.4 on either side. I want to try to make the diameter of my gear 0.8 smaller. So I'm at 87.2 now. Okay, that's too small. Okay, 108 actually works out perfectly. So let's try this and see what happens. Again, we'll make the hole. And we can see here that everything looks good. So now I'm going to export the STL. And usually when we export an STL in Fusion 360, we go up into the file menu and we export. But sometimes this is a little bit slow. What it does is it uses the cloud to try to make the files for us. And we might think that the cloud is fast, but often the case is our PC is faster. So what we want to do is open the gear that we want to export, open the bodies menu, and body 1 is the actual gear. If we right click on body 1, we can save as mesh. Format is binary, unit type is millimeter. I put my refinement to high, and we can push OK, and we can save the STL file. And this is a lot faster compared to cloud saving for me. I found that out 2 weeks ago when I couldn't export. It was taking so long, and it kept on failing on me. Okay, so now when we slice, we see that we've eliminated the gap. The gaps in the actual teeth themselves are fine. I wouldn't worry about that. We just don't want the gap between the teeth and the inner diameter. If it's too large, then it might affect the rigidity of the gear. So if we print at a layer height of 0.4, then we're getting about 22 minutes for the gear, and I think that's pretty acceptable. There's a few small things that I would like to adjust. If we try to print it like this, then there's going to be an issue with elephant foot. The first layer is going to get smushed and change the diameter of the bottom a little bit, make it a little bit less clean. Since we're using TPU, this is probably not a problem, but it's nice to have it cleaned up and not worry about it at all. So I'll just show you how to go about adding some fillets and some chamfers to this. What we'll want to do is we'll want to add a chamfer to the inner edge at the top and the bottom. And we'd also want to try to chamfer this edge at the top and the bottom of the teeth. And this inner edge here, we'll try to give it a little chamfer as well. If we look down here at the history, we can see this C pattern. If we scroll the history to before the C pattern, we'll see that we have just the basic wheel with one tooth. If we move the history to before the C pattern was created, we can edit the tooth, and that edit will be reflected into all the teeth later on. We'll try to keep our chamfers to 45 degrees when possible. So now this tooth is completely lifted from the bed. And we notice here that it didn't actually include that fillet into all the teeth. Go to C pattern, right click, edit the circular pattern, and here it says objects. And down here we can see that one body and one fillet is selected. Control select the chamfer that we made, and now we notice that all the teeth reflect that chamfer as well, and push OK. These things take a little bit of time. Let's put a small chamfer here. Try a chamfer of 0.4. So a chamfer of 0.4 is looking good to me. But you'll notice that if we try to select here, we're just getting one small segment. So what we want to do is we want to roll the history back again. And we'll put our chamfer in now. And we notice that it doesn't want to do the chamfer. And the reason is because there's a fillet. When we made our gear, there was a root fillet of 0.1. Now we can change this to 0. But when we create the gear, it often throws an error at us. So it's better to create the gear with a root fillet radius. Then we'll remove the radius, put our chamfer in, and then put the radius back in one more time. So here's the fillet. We'll just delete the fillet. We'll put our chamfer in. It's not so nice here, so I could modify this chamfer again. So this chamfer, let's make it smaller. Then we add a chamfer to this edge and to the main body. Yeah, and this looks a lot cleaner. Let's try 0.4. Then we need to put the fillet back in now. And when we're making these gears, if our corners are rounded instead of sharp, it can improve the speed a little bit because we're able to move around the corners with increased acceleration compared to making sharp turns. And actually, I want to test and see the difference right now. Okay, so we'll include our work into the circular pattern. It really takes time. Don't be surprised if it takes almost 1 minute. All right, so now let's export this mesh. Okay, so the additional work that we added to the gear increased the time by 1 minute. So now we're running at 23 minutes with sharp edges. So let's add the fillets inside and see what happens. I'll upload all the rings that I've created and leave a link in the description. Alright, so by adding in the fillet, we've managed to reduce the time by 2 minutes. 2 minutes isn't such a big difference, but it is 10% of this entire print. And the reason that this worked is because the fillet allows the acceleration to be higher throughout the print compared to making sharp stops. And this is where our acceleration and jerk times really come into play as well. So let's look at the parameters that I'm going to use. These are my standard PLA parameters right now. We'll go 0.4 for the layer height. We don't need a good amount of detail for this. We'll put in 2 walls. 2 is enough. What I found is that it's very rigid and still flexible enough to fit over the focus ring. So we will print with 3 layers. Infill I'm setting to 0. Using infill or trying to fill in the small tiny gaps to create micro strings between the teeth. So what we're trying to do is trying to, as much as possible, print in a continuous motion without needing to retract or hop or travel. The temperature needs to be changed, of course. So I print PLA at 195 and my TPU I print at 220. You might want to decrease the flow a little bit, about 90 or 95%, but print speed in the video that you've seen already was 50. But that's taking into consideration that my acceleration is set to 2000 and my print jerk is set to 15. So do we ever actually reach that 50? I'm not sure. There's a lot of teeth and a lot of movement, so we might not have time to accelerate up to the 50. So I do have my retraction turned on. I have my retraction set to 5 millimeters and the retraction speed at 65. This is what I usually print at, and I find that I don't have any problems in general. And when I print these gear rings, I don't have an issue like this. Now this one helps us a lot. Combing mode set to all. And what this tries to do is keep the travels over top of printed surfaces. So we're not traveling across the open center of the gear. We're traveling around the diameter of the gear. And it's keeping the nozzle over top of the print surface. And it's going to help prevent stringing. And it's going to help keep a constant flow. I'm just using my regular PLA cooling settings. Support was turned on from my last print, but we do not need support for these gears. There's no special adhesion needed, and I don't think I've enabled or played around with any experimental settings. So let's slice one final time. Okay, we're still at 21 minutes. You'll notice here that I have the Z seam lined up. Okay, I've actually managed to save 1 minute by changing the settings again. So the important point is to get the Z seam lined up. So using shortest and smart hiding should give us fast and good results. This turned out really well. In the center we have absolutely no stringing. The only string was on the final layer. And we can see that the string is barely attached. Let's take a closer look. The layers turned out really great. We don't have any large gaps. We do, however, have a couple little blobs, and these blobs are happening at the Z seam, so we could try to reduce the flow a little bit. If we take a look at the inside, we can see that the Z seam turned out really good. The layer lines are visible and slightly uneven. This is because we used a 0.4 layer height. This print was done at 0.2 layer height and 95% flow. We can see that the layer lines are invisible. We can see there's some extra stringing, but this is because I didn't have my Z seam aligned and there was unnecessary travels. The Z seam is right here, but on the outside we can't see any blobbing. Both gears fit and work perfectly fine, so it's up to you if it's worth double the time to print a little bit higher quality. I hope you enjoyed the video. Thanks for watching, and see you again next time. If you enjoy my content, please consider subscribing and give the video a thumbs up. It really helps a lot.